All right, let's start. So, what did you think of the yesterday's session? Was it boring? Was Fortran what you expected? You all knew what we talked about?
For me, I recognize a lot of it because I played around with Fortran a little bit, so
Mhm.
it was a good refresher.
Cool. I have to remember the cheat sheets, all the tests. Things that uh, left yesterday was start with you intro to Fortran, and we will and really get so it's not make you really yes, just if you how Fortran allocates them. So let's say We don't have many. I feel this is I think okay, so valuable as the slice. It for us. But will be say the the Line. In examples. Others. Data types. So as everything in Fortran, you the name. integer. After that, you can at any moment create two columns and the name of your variable. A column index and row index. Data type and create a using from this point access that pattern. Then the allocatable. You want to call this uh, all right. This to be Fortran in this version of Fortran. So we will element or not should they be order to all members of the look like. And number of rows was not part of 90 in Fortran '90. So from that point, because at this sign that is something local define a macro for from one. So for one, we create you know, so after that look like this should give us this. there is a program derived type array in the repository. I think it should be changed to I here. So let me try to compile it. Fortran. Right. So this is what I wanted. Now our vector is not really, we created a vector of arrays, but each element of this array, of this vector, is an array, is a matrix, but it's completely different. It takes different amount of memory, it has different amount of elements, and so on and so on. So when we print it, it's truly 1 element, 4 elements, 9 elements, 16 elements in given arrays. And that gives you some flexibility of creating and passing all of this information together with the data. Does that make sense? Yes.
How are you supposed to get the type information to say 17 5? Fortran you using files or something like that. How would you get that type of information to 13?
We'll talk about modules in a second.
Okay.
And that's how you're supposed to do that. So in what people were doing before modules were introduced into Fortran 1995 were two things. First was using something that was called common blocks that passed variables from that created a set of variables that should be shared between subroutines. There was nothing more horrible than common blocks, and everybody hated them horribly. And if you got code from someone that uses common blocks, it is really, really difficult to work with that. Unless you wrote it from the beginning and you actually know what the common block, what is in this common block and why is it there. It is sometimes these common blocks were as separate file that was included using per processor, but those are concepts that were really confusing and really making the programs not easy to maintain. Preprocessor is not part of Fortran. Preprocessor is the compiler thing that a mechanism that people were taking advantage to make their life easier. And we will also talk about preprocessor a little bit later. But the way to handle these things now is by creating modules. And modules are little internal libraries to the program. So you create yourself a file, call it something, and you say that in this file you're creating a set of functions, set of elements that will be you will be able to use later. And each function that needs to use them then needs to have a statement that, okay, I will be using that part. All right, modules. There you go. So what Fortran 90 has introduced is this beautiful way of getting rid of common blocks that Fortran 77 and earlier Fortran versions had. Module is a construct that allows you to organize logically code. You can split it to files. You can bring functions and derived types that logically go together into one piece of the code and call it one file and say that, all right, this is my module responsible for linear algebra. And everything that needs to be there should be sort of a self ways. and so there will be we may want to have choose different either when you create a wallet, you your thousands and you will call separate something the program. So
Oh,
the, the function you want to use all the subroutines available. You can also select only one that module and not this mode isolate things from each other. Here we define some uh, that in the uh, place in keyword in in if you compile this augment the visualize here as needs some other physics model that logic mathematics is right. Instead use model A, use the whole body of the program will work.
More you were dealing with several
Of definition of a module and before it contains a keyword and the definition will be available to the body 2 is placed to define. So let's into this I by 5 because I can I am assuming that this is a square matrix. In the programming in the functions that apply to that. That that do is we you use functions that you want to uh, so let's see how it starts on its ends here. And and it will assign all elements nicely that I can use. At any more? To the the right, that's only change the I really more of really past and will print it's to print and delete this way. But here you're completely skipping the argument. procedures, you're saying that the new name A from argument. How to overlay it needing all this example they can integer times. Follow what? This and them optimal. Likely it will not storing anything that's think about it. With the first item number 1. Uh, of marks. Unit 1 is the easiest one. Defining to be where they are. So element for single what needs a dense matrix use for the real matrix of this matrix is many elements function as far as them look like. That's huge. Call that function over and over. Or if you have times, yeah, as a side, that's what is used in standard template library. It is needing memory. elements, you have a million you have memory. Another thing that and see who's approaching passing memory. So my suggestion mechanism for students that special memory. So cells derive types mechanisms to control that problem. Can pass count. So if you look at the variable for variable for Fortran argument we have a command line arguments .fo3 code that does exactly what we have here. And if we compile it, we can execute it without anything. The command line argument count is equal 0. We can pass something. We have 2 arguments to the program. For arguments to the program, and so on and so on. Based on what it is, you can capture that value and control it, control the program with your own parameters. So it is a nice way of parsing all the arguments that were passed, making programs more flexible. Right, so this would look like this. Fortran has a nice, for a long time, a nice way of automatically handling list of variables that can be passed in as an input file. So it has, if you define all variables, let's say you define 2 integers and 2 real values, integer var1 and var2, real var3 and var4, you can create something that you will call a name list. The keyword with some define variable. Or keyboard is the name. Function. You can read the whole. That all the variables from if this works. We have this program name list input file. Let's compile it. We also have this file molecule input.dat with this input file defined. So if I now compile name list it will expect something to read from standard input, and I can redirect my file input.dat into this program, and that's what my program printed. All of these variables are now read, and all of them have assigned values. You can put reading one name list after another, and that will define you an input file for your program that can be passed very easily. Right? You can also control your program using environmental variables, and this may also be required, but for some things for your program, for some configuration parameters. You can read any Unix variables and value that this variable takes, and Fortran 2003 gives intrinsic function, intrinsic subroutine get environment variable for doing that. Environmental variable f of 3. We can get all these parameters, all the variables that are held using this variable name. So if you compile it, we get what are the values of these environmental variables, and those do not need to be system variables. They can be user-defined variables, whatever you need. Very often, when you're using some programs, you need to export some variables to make it to configure the program. And they will look for either certain files or license files or whatever in certain locations defined by environmental variables. Right? You can also, from Fortran file, execute a command line, execute any command in Unix. For that, Fortran 2008 brings function execute command line, and that lets you truly execute anything you want. From your program, you can execute other programs. This lets you extend the capability of your program by calling others and getting their output. All right, let's talk a little bit about to be called hello.x. There's a lot of a little bit different designs. Feature of variable. It can just do support it. To this process, while based. So that's the first step. We get the assembly file contains all the information the function please be even what should be the directives. The process directives as, as, as this. This things for what's of the we intended not so math in quality. We can steal something from algorithm value to put all of direct is also another one. Processor with file and at that moment values through to square root ish. You can move during the roads and try to avoid this really works. So we have this file. We have the file math.h that is truly defining all the mathematical values, and file math.f90 that only includes that file using the processor and print values of this definitions. Right, so let's try to compile it. And we'll get a warning. Illegal preprocessor directive. Let's see if it worked. Did it work? this is not what we saw on the previous thing. So it didn't. It's compilers don't take preprocessor as part of Fortran. You need to tell compiler very often to use the preprocessor. And let's see what we need to do really in Fortran to make it work. So each compiler has some assumptions what should be preprocessed and what should not be preprocessed. So there is an option to enable preprocessor, and that will be in Fortran -cpp option, and this will enable the preprocessor for absolutely everything. But Fortran has an assumption what should be preprocessed automatically, and everything that uses capitalized extension will be preprocessed by default. If it's not capitalized extension, it won't be preprocessed by default. So that may seem to be strange, but that's the convention people use. And very often, if you get a big package that was written in Fortran, everything starts with directory with source code files with capital letters, capital extensions, and then you end up with some build directory with small extensions after the preprocessor was run. So that's commonly used thing. We can use this option -cpp. Now we don't get this warning, and if we run math.hx, this looks more familiar. These are the more correct values than we got before. So preprocessor is something still you may need to enable by hand. Yes.
There's a problem using C different syntax for default type in Fortran is field for floating point. Default type for real numbers is field, not C constant. C is the opposite.
Those are not variables. Those are not variables.
Right, but so if you try to, I think if you try to assign that, so if you try, if you created double precision, stored M pi in it, you would only store single precision. But the rest of the digits would get chunked off.
Yeah,
like before you just put D0, right, or underscore.
Yes, and you can select what the this is compiler specific. To a literal. But if you, most likely it will default to what's the architecture of your system. So most likely the newer compilers will default to 64-bit integers and 64-bit real numbers to match them. So that will be the double precision and long integers. That's how modern compilers on HPC systems look like work. Now Fortran may custom to a single precision, and you may need to append the zero after all, or select different kind.
Yeah, it's single precision. Because otherwise it would print more digits.
Yeah, that may be single precision.
We got 15.
Well, we can see if if we change math.h and define this as d0, yes?
You have to change the type. You still need to change the type of
But those are not variables. It's the preprocessor that's truly replacing placeholder to number.
I forgot.
So that's why you were right. They were casted to single, and they were casted to double. Treats them as a double value. So you're truly, what you're truly doing is we're printing them directly. We're not assigning them to any variable. They are not variables. They're just placeholders of the preprocessor. So to extend the precision, that was a valid comment. You can use D0 or what's called the Fortran should use also a quadruple precision. Then you have all of them. So those are twice as long.
I think
Fortran 90 defines automatically one more higher precision, that's quadruple precision, and they are twice as long as double precision numbers. They're more accurate, and they're 16 bytes. So they will take much more, twice as much memory as the double precision number, but they give you higher accuracy and longer ranges of numbers. And that's the new part in Fortran 90 comparing to previous Fortran versions. In previous Fortran versions, that was a compiler specific, architecture specific thing. So Fortran compilers on Intel processors did not include quadruple precision, but Fortran compilers on other type of architectures included quadruple precisions. So for a long time, people that wanted to do quadruple precision in Fortran were doing that on Spark processors. This were the 64-bit processors even in the 80s, and they included the quadruple precisions. So whenever you need to do some precise fitting, for example, quadruple precision would be choice. Right? Any questions about this? And so this is what we did. We changed the value of the number from single to double to quadruple by appending the E0, or Q0 at the end. And that's single precision, double, quadruple precision. This is 32-bit, 64. Okay. With the preprocessor, you can also change the code and you can use preprocessor direct commands to pick one code versus another. So you can define yourself if-else type of structure for either including one part or another that will be controlled by user at the compile time. And at the compile time, to switch between passing often uh, so we take preprocessor should be used. Preprocessor .f90. We have this example, and let's try to compile it. We get these errors, and we can check what happened. And compiler truly skipped our preprocessor directive, and both of those codes are executed. So sometimes it gives you an idea what it means to skip compiler warnings when you compile some complicated code. You may get unexpected behavior. But if we include the -cpp option here, didn't complain, and now it included the block 2. If we look at the code again, and if we try to define this value, the preprocessor will include the first part and execute the first part of the code. So based on compile time directive, you can either steer one part of the code or second part of the code. For example, that's very often how libraries are enabled. There is, for example, if you want to use some external library, but you want to you have your own version of the library, just to provide as a complete package. You can use a preprocessor to steer it and let the user decide, or let yourself decide what you want to use. You want to use a library, or you want to use your own functions to handle things. All right, let's try this and see what happens. All right, so this printed what directives are enabled by compiler. We created an empty file, foo.f90, using touch command, and then we ran the preprocessor on it and we printed on the screen what happens. So this is how many directives how many variables are attached by compiler just to for itself to track its actions. And they will be specific for different compilers. They will be a little bit different. For example, what you get here is what's the processor type, what's the architecture type of this little version of storing values, what's size of different data types, what's the true version, the last version of the compiler that was used, and so on. So you can, for example, check what was used to compile and print given program. Also, you can, based on these directives, you can make different compilation automatically for different compiler. So, for example, if you're writing a really complicated code to support many different compilers, many different architectures, you may find out that there are some things that are compiler specific for no compiler and for Intel compiler and for any other. And based on one of these directives, each compiler will have its own stamp that you will be able to recognize. And based on that, you can say, all right, I'm being compiled with the GNU compiler, proceed with that piece of code. Rely on some things that's specific for GNU or for Intel or for something else. All right, CPU and wall time, just for measuring the performance. Fortran 95 introduced the CPU time function, a little subroutine, not function, and at any moment in the body of the code, you can call CPU time and give it a real value. And at any moment, at any other moment, you can call the CPU time again, give it another value, and just subtract this CPU. Access the wall. All time we have a system clock. Real values one that with the initial value and divided by the count, the clock rate, so ticks, and it into measure the CPU time. vector in. So to use it, create values. Let's see how it works, or if it works. Date and time. And it will print, it will access all of those values and it will print them on the screen. So let's Fortran. And it printed all the values, so year, month, date, difference from difference in the time zone, hour, minutes, seconds, milliseconds. You can combine them to something more. Right, so let's switch to pointers. Are there any questions about the previous things? If not, then let's switch to pointers. And Fortran 90 also introduced the concept of pointers for passing, for addressing the issue of passing things by reference versus passing things by value. And pointers can be defined at any data type, and any type and then it needs to be a variable uh, by reference. Right, so it, a using the will point with them basically nothing. After or it's only for empty field arrays. Uh, and keyword we can use memory field. I open something or not. It's part, right? Are there any questions to pointers? Yes. I'm sorry, why were they added to the language?
Yeah, what's the big advantage of having pointers? You already had all the array stuff plus make two variables point the same memory.
But that doesn't let you pass things by reference. So this was a fix of it says only this way. You always need to handle that. And here it's not direct. using. Okay. One thing that you should keep in mind about pointers is processor compiler and processor doesn't know whether two pointers point to the same thing or not. And this may have serious performance implications. What compiler can do for improving performance. So imagine this. If you have A, I, when you pointers, they can really B can really point to A, and the compiler doesn't know because it compiles a function. It doesn't look at the whole program. You know it, what you use, but the compiler doesn't know and cannot assume that safely. That this can be executed all at once, and then it will not make the efficient version of this code. And the efficient version is this. At the moment, the processors are organized a way that they can execute 16 operations at a time. So in that A array, and B, the processor could really take 16 numbers at a time and then in one cycle calculate all of the values. If it can assume that A and B are different, if it cannot assume that A and B are different, it's not going to enable that. It will do one value at a time. So pointers can seriously affect performance. And there are ways to fix it. This affects C more than Fortran, I believe. Less people use things Fortran than C. In C, or important is if you start using pointers, you can say that, right, A and B are always different. And the server type of processors that can really do more operations at one time have these vector units that can calculate more, execute one command on many different elements will be seriously affected. All right, make files. We're going further and further from Fortran, and so we'll start talking about things around maintaining Fortran packages. So imagine you have file that project that's more than one file. Divided your project into 3 files. It's complicated. And your that's the syntax to the computer. And that uh, G4 files really automatic. In the directory here, you have example. You have subdirectory called makefile example, and it has several files. It has config file. It has sparse algebra file with some way of defining sparse matrices. It has also sparse example file, how to use things, and so on. And if we can try to compile everything by hand here, or we can look at we can take advantage of make files, and you have a make file already prepared. This make file will not work. You have to a little bit modify it. But it looks exactly like the make file I showed you. And please treat it as a template for anything you need to do in the future. Modify it a little bit, and but the general structure of a make file will be always the same. So my compiler here was called gfortran-mp-49. We don't have that name. We only have the name gfortran. So please, before you use it, remove this mp49. You can save it now. And once you have the make file written this way, what we will do is type make, and that will execute this first target. As a dependency, it will proceed to preparing config.o, sparse algebra.o, and sparse example.o using the target, this target for .o files. and that will call the compiler with compiler flags. After all of that is done, this command will be run. fc flag source libraries -o, and that is our output called that will pick if we create a binary file program.sparse.x. All right, so let's try to just type make, and that's what happened. We executed these three commands. 1, 2, 3. The -c stopped the compilation at the object file. It didn't run the linker. This was compiled to an object. This was compiled to an object. This was compiled to an object. And after that, we ran Fortran on all object files, and we created a binary file from that. So at this moment, we have sparse.x and all object files together with all mode files here. So you take advantage of make files for making compilations automatic. Make files don't need to be for compiling things. Make files can be also for making the work automatic. So you can have, for example, your backup procedure, typing make, and it will do something for you. If you're using LaTeX for applications or your work, you know that this is a complicated. There's several steps into that. It's a compilation, then you run LaTeX several times, and you run BibTeX, and then you run LaTeX again. You can make it all part of a make file. You can write yourself a make file that does all of those things for you. So on and so on. Make files are truly generic. They're not related to compilation. What's good about make files for a big project is not only it makes it easier for you, but whenever you type make, it will only recompile the code that was modified since the last time. It will not recompile everything. So if we now, let's say, modify something, sparse example, let's say we modify sparse example, F90, and we'll only add one more empty line. Doesn't really matter how the modification will be. Save it, we type make again. It will only recompile that particular file and link everything together. It's not going to rebuild everything. This wouldn't be an issue with these free files, but if you have hundreds, that takes a moment. Right? So really going through step by step. First, we have the definitions of what we want to use, so we can easily replace those values by others. Then we have defined source codes, the object files that need to be created. And we have a definition what to do, the default our target that we want to execute, its dependency, and what needs to be done after dependencies are satisfied, and how to take care of the dependencies. So how to take care of the object files. You can reuse. Right, so when you run derive also, and defines length length defined and use them in a second. And but we need to see bindings. Specific make it and so on and so on. Available to create this integer type in C. Um, in the function called takes three integers and returns. And in Fortran, we want to use and C. We need to say this. Two arguments where the name of the C function underscore name. The name module ISO C binding written by review. Use this function. Not and we can look at this example in the repository. You have file. You have subdirectory called C Fortran example. And there is the example that we really looked like a second ago. And there is a C function that looks like this. And there is a make file that supports both of them. So the make file now looks like this. Again, we'll have to change the compiler names. But it's defining what's the Fortran compiler, what's the C compiler, what is the program name, what are the source codes or object files for Fortran and for C, and what is the default target. The default target now has two dependencies. One is called F SRC and C SRC. So those are the dependencies. We have the target for .o files when they end with F90 extension, and the same with C. We have different definitions how to handle them. And after the dependencies are satisfied, we run Fortran compiler. We include all the objects and we link it to the program. So let's see what's going to happen when we type make. Before we do that, you need to modify this file a little bit. Remove the MP49 from both of those compilers to have only GFortran and GCC. Have only GFortran and GCC. Okay. And when we type make, the program will do this. The first thing it will do is it will call GFortran, compile the example F90 to object file, then it will call C compiler, compile the C code, then it will link all of them to an example file. Let's see if this works. So what we were doing is adding 1, 2, and 3. And we got 6. So at least we got the correct value. Right? Any questions about this? About make files in general, about mixing languages, when, why, when, what the heck for? Yes. The Fortran lets you define what what's the underlying Python. Sorry, Python lets you define what functions can be called from other languages, and most of the things can have Python interface.
Some libraries how a function uses a function of that function.
And if you just quickly look at the examples that we have, you should have a function as an argument. Yes, that's in with the interface. And you have this example where we have two functions, linear function and quadratic function. They're both real functions and they're passed as argument. So that's like passing function as a pointer in C. Now mixing two languages into that will be a little bit more, there will be one more interface on top of that. All right. Let's talk a little bit about the compiler options. Nowadays, there is every big compiler suite has a Fortran compiler, and the most commonly available compiler would be Gfortran that comes with the GNU package. There is more compilers that you can have on your systems. On Palmetto, for example, we provide also an Intel compiler that has been developed, is a proprietary compiler developed by Intel, and more computers like Palmetto that are made by big vendors have proprietary vendor Intel knows a lot of things that Intel knows how to performance Fortran Intel compiler is for your job. There is also any workstation is but let's look at the compiler functions. Will be only dash O language 7 Fortran 2000. This is that's why there may be some issues with uh, uh, you can think performance programming in a second. Using that optimizations for, for interchanging vectorization. For a GNU compiler, to uh, um, the feature code may not be portable at all. Between the enable the process function map targeting performance use of my version. That is experimental. Performance. Right. So if you enable OpenMP, if you parallelize by you can uh, size functions, the assembly code. CPP, all of them, all of them is just the flag relations yourself to handle things like that rely on basic linear mathematical vector. La PAC is the lead that defines functions for linear equation. So, the good look into what BLAS and LAPACS take that part of a processor can handle them. That's some uh, for this function, dgem, from uh, or any other. The same with this how it passed uh, uh, what whether you want to pass or another. Coming rely class in la pack to that. Not try to fix the optimal and variables if you do that, it will in the loop. Depending on compiler. The other to how data should be orchestrated. All right, so that's all what I had for you. Please treat these programs that that I give you as place that you can steal from. Don't if you look there how things are done. All of them work. Treat them as something to you can start with, and you have all the handouts in this directory. Um, don't think that if you don't remember any syntax now you won't be able to program. Syntax is trivial. You can always look up keywords. That's not the point of programming. Uh, pick the best language that's appropriate for your program. Don't write web scraping programs in Fortran. May be more difficult, but do any scientific application that is really time consuming in Fortran. It will be much easier to get things done quickly. There are certain assumptions in Fortran language, like passing by value, that really make it easy for compiler to optimize things. It's not that Fortran is magically much faster. It's not that compilers pay more attention to Fortran code than others. It's not that. It's how the language was written, how the language was designed. And since it has this long history, it carries a lot with it. It's much easier to write performance program in Fortran at the first pass than in any other language. It's easy to optimize Fortran code, a little bit easier than any other language. Fortran really evolved over the last 20 years, and there is object orientation. There is it allows you to define your own data types. The version of Fortran 2008 also has built-in parallelism. We didn't talk about that. It's something that's called coarrays that lets you do things in parallel. It has its own mechanism for handling parallel calculations. It's really still developing. It's not a dead language. Many people think it is. It's certainly not in scientific computing. All major scientific programs are written in Fortran. If you watch weather simulations every night, weather forecast, those guys are using Fortran to calculate weather reports. All major chemistry programs are written in Fortran. There's only a handful of them written in other languages. So all the drag simulations and all the material simulations are done in Fortran. Or earthquake simulations and predictions, everything is that really touches performance. It's mainly still Fortran. Any questions? Yes.
The use of makefile only comes to play when we have more than one source code.
If you want to make it so if you write yourself a makefile, I use it when I have more than one file, but it's really supposed to make you make the compilation simpler if it's a difficult command. So if you have something more than Fortran and the file name and then the name of the binary, if you, for example, need to link to a lot of libraries, this will make file there is make files at once on formatter, for example.